Now that we've built the ceiling and the floor, it's time to build the walls. My original ceiling height was 102 inches. Now that I've actually built the structure, it's 101 inches. Now it's time to go back to the design and figure out what the dimensions of my room are based on my room ratios. The problem that I'm having now is that now I'm slanting the ceiling this way, and I've realized that the floor is slanting this way, which makes sense because in a basement the floor should go towards a main drain. This complicates my design because I have this angle and this angle to contend with. The solution is to average the ceiling height. Measure the ceiling height in all four corners of the room, add together, and divide by 4. My new ceiling height is 99 inches. We can use this in the room ratio formulas to find my width and my length. 99 times 1.618 is 160.18 inches. That's my new width. My new length is 1.414 times the width, which is 226.49 inches. In my particular case, I know the back wall will not move, so I'll start by setting the bottom plate in place for the back wall. Remember that we use concrete expansion joints for isolation from the concrete wall of the existing structure? The expansion joints are also a guide for our bottom plate placement. The idea is to use a screw that is long enough to go through the 2x4 bottom plate and the subfloor and possibly into a hockey puck, but it's not so long as to go into the concrete slab. Pre-drilling the holes will help in the installation and will prevent wood splitting. Just choose a bit that is slightly smaller than the width of the screw you are using. If you're using drywall screws, then use a 7/64 or 1/8 drill bit. The front wall is to be 226.49 inches from the back wall, but we also need to add a 1/2 inch for the drywall on the back wall and another 1/2 inch for the drywall on the front wall. Depending on what thickness of drywall you are using, be sure to account for the thickness at both ends when making your measurements. In my control room design, I decided to mount the drywall directly onto the studs. If you use RC, you need to account for the thickness of the RC as well. So 227.49 is where the bottom plate for the front wall will be. Measure that in 2 locations and snap a chalk line between those as a guide for the installation. The left and right walls of the control room are supposed to be angled by 3 degrees by design, but I have a support pillar that cannot be moved right here. The actual angle of the left wall will be determined by that pillar. If you don't have restrictions, just measure the angle and build the bottom plate out to the front wall mark. Hold in place with a few screws, but don't put them in all the way just yet. We need to make sure everything works first before we fasten it down permanently. Once one wall plate is in place, then we measure the actual width of the room, in this case 160.18 inches. Don't forget to account for the 1/2 inch drywall on 2 sides. Add this to your measurements so that the inside of the room is the right measurement. Now we can measure diagonally from that corner to the opposite corner where the front wall plate is going to be. For my room, this is 271 inches. Then I can make the same measurements from the other corner, and then the 2 walls will have the same angle. Then we can snap a line on the floor, and we have our guide for the installation. Next, we have to find our front wall angle. So we go back to our design and update the angles and measurements. And we can see that the angle we need for the front wall starts at 205 inches from the back wall. Next, we find the center of the front wall. In my design, the front wall measures 134.25 inches. Divided by 2 is 67 2/16. Measure that out, and that is the center of the front wall. Now we lay down a 2x4 at 205 inches on the left wall, and then 205 inches on the right wall. And where they cross the center line, that determines the angle. By design, it should be a 60-degree angle, but in actual construction, our angle is 61 degrees. With these 2x4s in place, you can mark the angles to cut on the wall plate, and then for the angle plate, referenced against the front wall chalk lines we drew earlier. Make the cuts with a circular saw, and the puzzle fits together nicely. Now we can measure between the 2 angle walls and cut the front wall plates to size. Now we have the finished bottom plate laid out, and we can lock it down by putting a screw every 12 inches or so. The top plate will be the same as the bottom plate, same angles, same measurements, but to do this right, we use a plumb bob to find the corresponding point on the ceiling as it is to the floor. Place a small nail at that point, then find the corresponding point at the front wall. Snap a chalk line between the two, then you have a guide for the installation of the top plate. Pre-drill and mount 2 screws as we had done when building the ceiling, and run those in to hold the top plate in place. While referencing your RC markers, put the screws in on the RC channel and not into the ceiling beam. Putting in stud work is labor intensive. This is where a good nail gun will come in quite handy. You can put them in with drywall screws, or you can pound in some nails, but a nail gun will make everything go a ton quicker and is a lot easier. Just make sure that you measure each stud individually, as there may be some anomalies in your floor. You can use at least 3 nails to hold the stud in place, 1 on one side and 2 on the other side. Line up the bottom first and shoot a nail into it to hold it in place. Then use your level to make sure they are straight from side to side and back to front. Never assume that if it looks straight or lines up that it is straight. Use your hammer to gently tap each stud into place. Place another nail in at the top and double check your framing. If it's good, then put in the other nails. Then place a stud every 16 inches on center, which means that if you measure from the right side of one stud out 16 inches, then the right side of the next stud will be lined up on that mark. After your studs are installed, go around and mark on the ceiling and on the floor where each stud is to make it easy to hit when you're installing the drywall. We use black spray paint for this. Steel studs are an alternative to wood. I used both in my construction. RC doesn't improve steel stud isolation because steel studs have inherent resiliency as they support the drywall. Generally, steel studs isolate better than wood, so the decision is completely up to you. Like wood, you start with a base plate. You cut the length with tin snips and then bend it up to make a right angle. After the cuts have been made, you can put a bead of construction glue on it to hold it in place. Then use small drywall screws to go through the steel and into the subfloor, but not into the floor of the structure. The top plate can be installed in the same fashion as wood, by using a plumb bob to find the corners and to make a chalk line. Steel studs are completely straight, so there's really no need for a chalk line here, but I find it helps to clarify that everything is in the right place. Then place a bead of construction glue on the top plate to hold it in place. This is one advantage of steel over wood, is that they can be glued in place and run the screws in later. Well, now you're ready to put the studs in. Just like with wood, it's important to measure each one individually, but the advantage of steel is that it doesn't need to be as exact. It can actually be within a 1/4 inch of exact and still work out just fine. Once you have your measurement, you snip both sides with tin snips, and then cut through the middle by curling the studs with your free hand. This makes it easier to cut all the way through. Place the stud in the right angle end of the base plate as shown. Hold it together with this special vice grip, then fasten it with 1/2 inch number 8 panhead screws. Doors and windows are a big concern in acoustical construction because they compromise the integrity of your design. The sound isolating properties of your walls will never be any better than the doors that you put in them. It's for this reason that you want to figure out what the sound transmission class is of your doors first and build your walls to match. In my particular case, I already owned 2 sliding glass doors from a previous studio. I also have the advantage that my main tracking room is a floor above me. It's for this reason that the room next to me is an overdub room. I figured that I wouldn't be making much noise here in the control room, and I certainly wouldn't be recording loud rock bands in the overdub room because it's too small. So my solution of 2 sliding glass doors provides some semblance of sound isolation, but also allows me to have a window into the other room. So this works for me. In order to make the threshold of the door flush with the floor, I needed to look at my construction and found that if I cut my subfloor and recessed the door, it would be perfect when I finished the floor with the bamboo flooring I had selected. This means that I need to cut the subfloor, place a few more hockey pucks for the door to rest on, and seal the whole construction. We made the cut in the floor with a circular saw to start, and then finished it with a jigsaw. The jigsaw blade is longer than the depth of the floor and the puck, so I used another piece of subfloor to lift the jigsaw up so it would clear the concrete below. Since we are in the mode of cutting the subfloor, it pays to take this opportunity to cut the subfloor between your control room and the adjacent room to provide isolation between the 2 rooms. We are following standard double wall construction techniques, so using the circular saw and cutting the subfloor gives 1/8 of an inch of airspace between both rooms to prevent acoustic short-circuiting. Once the cut is made, then we can put more pucks down and place a bit of glue on them to fasten them to the door. Pop the door in the trench and fasten it to the wall. Now notice that when we put in the finished floor, the threshold will be flush.